168, and hopefully I don't have to use that thing, it's horrible. As far as a reminder, start to look through the rest of Chapter 5, although I know you're hopefully focusing on the exam, but we do have to keep going, otherwise I have to speed talk. I don't know why I look up there, I have it in front of my face. This week's lab is Color by NanoWorld, and I would, again, open up that page we did on Friday and remind you about the changes, but we can't open that up right now, so don't forget we are not using the spectrometers to capture spectra. You do not need steps 4 through 7 procedure. We essentially just made it into a qualitative lab, or got rid of the quantitative part to make it more understandable to you. At a minimum, procedure is sufficient to conduct the new experiment. Don't forget there are suggested data tables that hopefully your TAs emailed to you over the weekend since you can't give them Canvas. Also, you need to have your pre-lab assignment completed. We know we have a quiz on Friday. It will be a group quiz. If you don't want to work in a group, that is perfectly fine. I will have a better idea, hopefully tomorrow, if I can get it to Canvas, what will be on that quiz. If I have to, I'll just email you through Outlook to let you know, but I do have a bullet list ready. Exam 2, we're aware, is Thursday, 5:30 p.m., 60 minutes in Lapham, not in this room, section 3.6 to 5.5. I did put some new lecture activity things there. I don't know if we're going to get there since I'm really trying to stall right now because supposedly somebody's going to be coming in a second and hopefully get that thing going. Text me? No, not yet. And we did put some new Moodle Exam 2 homework problems there, but again, I'm not sure how far we're going to get. Are there any questions that you have? Yes?
Are we going to do the end of the exam and stuff today?
Yeah. It's really 10 minutes maybe, and I can probably do it without the papers.
It's just the partial questions, right?
Yes. Anybody else? Yes, over there.
If Canvas is in fixed by Thursday, we have actually done
Well, that is not through Canvas, though. Oh, the links. I will send you the links. If it doesn't get back up again, I will send the links to everybody's out. Okay, so that question was about the extra credit links, and thank you for bringing that up. So I'm going to send myself representative right now to send that calculator link to everybody in case you didn't get a look at it. Thank you very much for actually asking that, because with everything else going on this morning, I kind of forgot about that. Anybody else have any questions? Good? All right, hopefully Amazon will get everything figured out soon. All right, so where we're picking up is section 5.5, Dalton's Law of Partial Pressures, meaning we are on number 1, page 168. But actually, let me see something. Do I have my COVID extra slides here? Oh, I may have got rid of some of them. Okay, so hopefully I don't have to write on the dry erase board, but I might have to. We'll see. I don't know if markers exist in this room. I never use them. All right, so partial pressure is simply the pressure a gas in a mixture would have if it was by itself. So they have asked you in number 1 to diagram a mixture of argon and neon on the particulate level, so basically what I have here. And if pressure comes to the collision of the particles inside of their container, which of these two gases would have a higher pressure due to its own particles? Argon. There's simply more argon particles. So pressure is directly related to the number of particles, and Avogadro's law is the second version. And it's a very important relationship, which is why I had to slide it in there as an extra page. So when we're thinking about mixtures, we're just thinking about really the partial pressure, the pressure that those particles are actually producing due to the collision. Sorry, little step right out. As far as A, what is the pressure of argon? Called the partial pressure of argon. P, so argon due to, just to make sure we're all understanding, is due to the collision of the argon particles alone. Okay, if anybody wants my pages, just send me an email. I will send them to you today, especially since we're at a technical difficulty. The partial pressure of neon, P sub neon, would simply be due to the collision of the neon particles. A more useful way to think about partial pressure is something I've already said. The pressure that a gas would exert is occupying the container alone, meaning we can still calculate it using the ideal gas law. And that's what I was looking to see if I have the COVID slides, and I don't seem to. So, we know that PV equals nRT, and I'm very sorry if you can't see that well. Therefore, the pressure of a gas in the container would just be if they're thinking about the partial pressure of argon, that would be piece of argon, what particles are we going to count? Just the argon particles, so it would be the moles of simply argon. There's the equation for partial pressure. They also ask you at the bottom of page 168 to write it for the neon. So the partial pressure of neon, piece of neon, would simply be equal to the moles of neon times R times T divided by V. Pause for a second. I don't know where this cord goes. I unplugged one thing and everything went off, so I don't think that was the right thing. It just simply, I put it in and out for 4 hours. I didn't restart this whole thing. Restart the computer. So I have no idea. So you can fiddle around all you want. I like to write that, sorry, unpause, as a generic equation because otherwise sometimes students get it in their minds this is only for argon and neon. And I'll put the generic equation over here so it can stay up for a while. The partial pressure of whatever gas you're interested in is equal to the moles of that gas times R times T divided by V. That way it's not specific to argon or neon. Any questions? Because now we are labeling the pressures a certain way, on the top of the next page for number 2, they have a piece of TOT type for you, meaning total. Well, we know that the total pressure is going to be the same equation we started off with, would be the moles total times R times T divided by V. It's just now that we have subscripts on some, that you might forget what it is if you don't have the TOT for the total pressure somewhere else. Any questions? Yes? Did I miss something? We were going to get to that, and maybe I did miss something, I don't know, but no, we cannot. We have a nice image that goes along with that. So the question was, can partial pressure, right, be measured with a pressure gauge? No, because the pressure gauges cannot tell the difference between these the different particles. They can't tell, oh, this is argon or this is neon. Anybody else? All right, so I did put the slide right with that hand went up. The definition of Dalton's law of partial pressure is simply the total pressure of mixture of gases is simply the sum of the pressures that each gas would exert if it was by itself. The reason for that is pressure is directly related to the number of particles, and hopefully it makes sense that the number of particles is additive. So if we want the N total, that would be, for our argon and our neon example, the N of argon plus the N of neon. Well, if pressure is directly related to the number of particles, we could simply write, I don't like writing low because people sing it back. P total, now let's do D, sorry, equals the partial pressure of our argon plus the partial pressure of our neon. And I know that in number 3, AB, they kind of do it in a slightly different route. I find it's easier for most students to kind of understand if we add the moles, but that makes sense. And then connect it to the pressure. I know in A, they say, how can this be shown using an equation? They have you combine a bunch of these to get the P total equals P argon plus P neon. But I just learned through the years that students kind of understand this other route by doing B first, where it talks about moles. So I did not try to confuse by doing that. Any questions? Okay. Thought so I had. In C, they want us to focus on only one of our gases as part of the whole, and they have the P total type for you. So they're asking you, where'd my total go? To write this equation, N total RT over V, and then they have the P argon. I'm actually going to move our argon. Actually, I'm not going to move our argon. I'm going to move this guy over here. I want to keep this generic one. I'm going to erase that part of the board in case you need anything. What we're going to do is we're another equation for partial pressure using those two. Because we can see that if we would combine these somehow, we could solve for the partial pressure of argon, which could also be true for any partial pressure of any gas, meaning P sub A. All right, in D, it asks us to give the ratio of these pressures, meaning we're going to divide the two equations by each other. So they want P, oh, sorry, they had neon type, I put argon. That was about to be a hand, good eyes. Sorry, they had the neon type. We could do it with any gas, but I don't want to stray too much from this since they've already enough of a change. We're going to divide the two equations because they want us to basically find that ratio, this over this, which is what they have in parentheses, meaning we're going to divide these two. I'm going to rewrite so it's a little clearer. So P neon over P total would equal, in my numerator, I have the other side of this equation, N neon RT over B, and the denominator I have on the other side of the other equation, N total RT over B. That's basically what they're asking you for initially in part B. Can I cancel anything out? Did I hear RT to B, I think? Yeah. These gases are mixed in the same container, right? So they're going to have the same temperature, the same volume, and R is simply a constant. Meaning I can simplify this to partial pressure of neon over total pressure would equal the moles of neon over the moles total, which further shows how pressure is directly related to the number of particles. Any questions? We have a new definition before we continue with this. Mole fraction is one of those concentration units that I had up on the screen before we started talking about molarity, right? It's dimensionless, meaning there are no units. It's a quantity that expresses the ratio of the number of moles of one component to the number of moles of all components. Well, wouldn't that be this ratio right here? Moles of one component over the moles of all the components. The variable for mole fraction is a big X. So if I wanted to represent that with that variable, the mole fraction, big X sub neon, equals the moles of neon divided by the moles total. Meaning we're putting that ratio into a variable to simplify the equation when it does end up confusing people then because you forget the variable means. If we substitute that variable in, we can further simplify our equation to P sub neon divided by the total pressure equals the mole fraction of neon.
Argon?
Neon. I accidentally wrote argon at first, but they had neon typed for me this whole time, so I switched it. Maybe you didn't catch that. I didn't want to confuse everybody, but I ended up confusing you. Sorry. It's any gas. It doesn't matter. We can solve for the partial pressure of neon. P sub neon equals the mole fraction of neon times, multiplying this up, the total pressure. Meaning, in terms of a generic equation, the partial pressure of whatever gas you're interested in equals the mole fraction of that gas times the total pressure. Questions besides the confusion about argon versus neon? What else is mole fraction equal to besides the fraction of the moles? It's also equal to the fraction of the pressures, right? Yes, sir.
If we have the partial pressure of neon putting over the total, why are we solving to get the other half? Partial pressure of neon over total equals, moles of total.
Moles of neon over moles total.
Got it.
Meaning these are now two different ways to find a partial pressure, and the difference is the information you're given, right? For the first one, based on the ideal gas law, you need to have the moles of your gas and the temperature and the volume. For the second one, derived derived from the ideal gas law. You need to know the moles of everything you have, the total pressure, but you don't need to know the temperature and volume. So it really just depends on the information you're given. That make sense? And I think that's actually brought up in the next page. So yes, the top, page 170, because we cannot measure a partial pressure directly, thank you for that question earlier, what are two equations that we can use to calculate the partial pressure of neon or any gas? I don't like having students just focus on the neon. It's any gas. Those two equations. But underneath it says, in J, what do we need to know to do this? Well, for the one from the ideal gas law, we need to have the temperature, I'll put a little dot, the volume, and the moles of our gas. For the one coming from this, we need to know the moles of our gas, the moles of all the other gases, so we need to know all of our moles, and we need to know the total pressure. So total pressure and moles of all gases. I kind of just went with my head, which was the next thing. We have the visual that is in K on the next slide, which is usually what reminds me to say, or actually ask the class, can we measure partial pressures directly, which already came up. So we can see if we separate the two gases, then our pressure gauge is reading the pressure of those gases due to the collision of the particles with the inside of the container. Once we combine the two gases, that pressure gauge is just still going to give us one pressure. It's going to be the total pressure. It can't distinguish between the individual particles. So underneath the image, at the bottom of page 170, they ask you what properties can be measured for the container on the right. What measures must be calculated, cannot be measured. So the container on the right, well, if we knew the size of the container, we could calculate the volume. We could put a thermometer inside it and get the temperature. We can measure the total pressure, but we have to calculate the partial pressures once we mix the gases. The gauge just simply can't distinguish between them. Any questions? Since obviously it wasn't just me not knowing how to plug something in. That is, draw a line, the end of exam material. So I said it wouldn't take long. I think the technical issues made it a little bit longer. So partial pressures, mole fraction, in simple terms, will be tested for the exam, and there's some of that on the review as well. Complicated things, like number 4 on page 171, no, not huge problems. Are there any questions that you have in your heads? Yes?
Could you find one of the partial pressures using the other one in total, theoretically?
Yes. So if you knew the total pressure and you knew the argon, then you could find the neon.
Okay.
You would just subtract one from the other.
And those would equal the moles, right?
Proportional to.
Okay.
One's an ATM, right, and one's mole. So they're not equal numbers, but they're proportional to each other. If you knew the mole fraction, you can then, and you know the total pressure, of course you get the partial, but if you knew the mole fraction in the neon, you can get the total. Or realize the mole fraction is this, you could solve for any one of those. Okay? So the ratios are equal to each other, but not the individual measurements. Anybody else? I just thought of something else I have to send you via email in case campus doesn't go up. Knowing the exam's Thursday, and I was just about to ask, which is what reminds me, how many people have already gotten the exam review before campus and the internet crashed? Not everybody. I will put that in the same email that I send those links. Okay? Because really more important than reviewing is that extra information page is the same one that you'll be given on the exam. So this way you'll know exactly what equations are given. Any questions you thought of? I was hoping he's going to get that working. I guess not. It's not, it won't go on. So it wasn't me. Ideally, we would have done this problem next. I don't think this board is working the best, especially for people sitting in back. That's, can you see okay back there? Nobody wants to answer. Nobody wants to do anything else, right? can kind of see. Thank you at least for giving me a N, which is what I thought, which is why I don't use the boards. Because they're too narrow and they're too low and, bless you. Meaning, that's that problem. We'll do that on Wednesday. So let me continue my notes. So number 4, page 171, Wednesday, there's lots of little stuff in there that is testable, just not the entire thing. Meaning, if you look through the problem, oh, we're balancing an equation. Oh, we're applying a scaling factor. Oh, look at that, we're converting temperature. We're doing some partial pressure equations. But then there's a limited reactor, so there's nice little exam review things in there, but please, the reason I told you to draw the line before that is I didn't want you to think a big problem like that would be on the exam. So let's go to 172. We will look at 171. This I can still use the PowerPoint for. Number 5, does partial pressure change with container size? Volume's in there, so it's got to change, right? If we have the same number of particles of our gases and we put them into a bigger container, there's more surface area, right? So the pressure will go down because pressure is force collisions per surface area. So yes, when a substance is in the liquid phase, are there also particles of gas, technically vapor, present? If it's a volatile liquid, remember I did touch on the idea of volatile when we were wondering why water wasn't listed on that one table, although it does vaporize, we have humidity in the room. So that's a beaker of water. You can see the water molecules. If we put a lid on it, we capture vapor in there, and the process of evaporation and condensation continue to go on until we hit a certain pressure inside that gas area in the beaker, what I would always call the headroom, the headroom in the beaker. This is not, well, it's partial pressure, but it's a different type of partial pressure. That, in the beaker, and the pressure we would read in the headroom is called vapor pressure. That's the partial pressure of a gas above its own liquid. I will write the definition, although I don't think anybody can see it. So vapor pressure is the partial pressure of a gas above its own liquid. And notice I clicked in a table from our textbook, from chapter 5, table 5.2. It says pressure of water vapor at various temperatures. There's no mention of volume. Vapor pressure is independent of volume. And the reason is, if we put the water in a bigger beaker and cover it, we'll just get more evaporation until we get to the pressure for the particular temperature we're at. Maybe we'll get more particles in the gas phase to increase the number of collisions for that larger surface area, but it will stop increasing once it hits a certain pressure, which is only dependent on temperature. So for C, will the partial pressure of a vapor above the liquid of the same substance change container size? No. Put it in a smaller container, you just get less evaporation until it hits that particular pressure, in which case we'll have a constant both ways, arrows going, evaporation and condensation, but we don't get an increase or a decrease in the number of particles in the gas phase overall. Net, nothing changes. Hopefully it makes sense that either of these ways of thinking about partial pressure does depend on temperature. Whether it's our PV equals nRT version, we have temperature there. We don't see it here, but it kind of is there. It's hiding. Remember, we crossed them out. And this one, it makes sense, yes, it will change with temperature. In either of these want us to be able to read the table. What is the partial pressure of water at 55 degrees Celsius? Notice it has a reference to the problem we're going to do on Wednesday. Well, if we look at 55 degrees Celsius, if we go over, 118.04 millimeters of mercury. Guess what? That's almost the answer we get when we do the problem on Wednesday. Although, volumes can be different. And then they want you to read it again. What's the partial pressure of water? 25 degrees Celsius, 23.76 millimeters of mercury. If you come across a Moodle problem where you need the temperature, the vapor pressure of water make sure you use the table from our textbook. If you Google, you can get various answers which are all close to each other, but they are measured values. Another problem we're going to do on Wednesday is this one. We'll talk about the experimental technique, but we can't, of course, do number 7 on page 173. Not fair to you for me to write on boards for a problem. Wetting of a gas. This is a very useful experimental technique because gases are something you could lose really easily. They're really small, they get lost. What are we doing? Well, we have some potassium chlorate and manganese fluoroxide in our test tube. Notice there's a stopper on there and a hose coming out. We're taking the hose, we're putting it into a water bath and putting it up into an inverted bottle. The inverted bottle is a very easy, cheap way to collect the gas. Why would Dalton's law of partial pressures apply here? Well, we will have, yes, the oxygen from the reaction that we collected, but we'll also have water vapor. Because by inverting that bottle, we have headroom there, and we'll get some evaporation of water as well. The P total in this case is going to be the pressure of the oxygen for the particular image, plus the pressure of the water particles in the gas phase, and all we have to do is go into a table and look up what that pressure is. And per a question we had earlier, then you could just subtract to get the pressure of what you were actually interested in, this particular reaction, the oxygen product. So we'll do that problem also on Wednesday. It does contain some nice little review things as well, such as converting pressures, remind about partial pressure, calculating moles for P equals NRT. So nice little review snippets there as well, balancing a reaction, calculating moles of a product from a reactant, moles of a reactant from a product, and then, using molar mass and density to bridge between moles and volume. So it's a nice little review problem as well. Any questions? Yes?
For the water vapor, why is it in millimeters of mercury instead of ATM?
Because I think the textbook author just chose to do that.
Okay.
We, of course, can convert to ATM, which is one of the things they're having us do in the problem. Maybe he wanted the instructors to have a reason to have students practice. I'm not sure why he chose that unit. Anybody else? It's a good question. You never know if there's a real reason why versus author's choice. Okay, let's see. We can't do that one either. No, we're not doing that one. I do still think it's valid to have the page 176, which was on the electroactivity list, still as practice problems for those who do dedicate time to doing that, because there's something about partial pressures there. There's a chapter summary problem, which living reactants along with partial pressures, and then there's an exam 2 homework problem, which I think also got on the other list, plus a question from previous exam. I hate doing this, but I don't want to start the next section without the pages. Because we're going to get a little behind you that, but it's too confusing, and I don't want you to think about it right now. I want you to focus on the exam, okay? So I'm